Welcome to lecture number 33. In the last lecture, we have seen two equations. One is the relation between the efficiency of energy transfer with the distance r, that r is the distance between the donor and acceptor. And another equation what we have seen, this efficiency of energy transfer, right, that is coming out either from the decrease in the fluorescence intensity of the donor in presence of acceptor, or the decrease in the lifetime of the donor in presence of the acceptor. Right. And we also have seen that if we now plot this E, the efficiency of the energy transfer, as a function of r, the distance between the donor and acceptor, that shows a typical sigmoid type of curve. Right. So, as it is evident from here, let me draw and then we will discuss. So, that curve what you saw is something like this, and here is my 1 and here is my 0. If I plot E and here is your r, and here is 0 r 0, here is your 2 r 0. So, you see this efficiency of energy transfer, this capital E, is very sensitive in this region, very sensitive in this region, right, very sensitive in this region. Little bit of change of R will change this E drastically, right. So, now I can tell you on the other hand that if you now can experimentally determine this E, you will get some idea of this R, what is the value of R. If you know this capital R 0, and this capital R 0 I said is a Forster distance, and this Forster distance for a particular donor acceptor pair is fixed. Right. So, situation is something like this, right. I have to determine this capital E, the efficiency of energy transfer experimentally, and then R 0, the capital R 0 has to be determined in beforehand. Then for a given measurement, if for a given value of capital E, it is easy for me to comment about the what is the distance between the donor and acceptor. Clear? That is why this energy transfer process are widely used in biology, and this is also referred to as the molecular ruler. So, using molecule you can measure a distance, right. So, it is referred to as molecular ruler. Also, one thing I should mention over here, that this is energy transfer, that is for sure, as we are discussing from the last two lectures, and this energy transfer is possible only when the emission of the donor is in resonance with the absorption of this acceptor. The energy should match, otherwise it is not possible. That is what I said, right, and you have seen. In this case, the interaction between the donor and acceptor is by the Coulombic interaction, and which was introduced by Forster for the first time. So, this process is known as Forster resonance energy transfer. The short form of this FRET is very popular among the biologists, because it is a procedure by which one can determine a very small distance, and it is very sensitive to the distance. I mean that efficiency of energy transfer is very sensitive to the distance over this region. As I said, over this region it is extremely sensitive. So, a small change in the distance will give a large change in the E, right. So, you can use this E to measure very nicely or very accurately the distance between the donor and acceptor. So, this energy transfer is actually called this FRET, which is nothing but Forster resonance energy transfer, and as I said earlier that this E can be measured experimentally. So, this is equal to 1 over I dA. What is IDA? Intensity of donor in presence of acceptor divided by ID, which is again same as 1 minus tau dA divided by tau d, again same lifetime of the donor in presence of acceptor and lifetime of the donor, this tau d is lifetime of donor in absence of acceptor, right. So, you can determine this, and I also told you that this is equal to k E t divided by tau d inverse plus k E t. So, I can simply equate this with this, right. So, if you do so, what you will going to get ultimately is k E t is equal to 1 over tau dA minus 1 over tau d, right, just after simplification. So, the result will come like this way, right. Now, experimentally you measure this guy E, right, or experimentally you measure this tau, experimentally you measure this tau, the lifetime of donor in presence of acceptor and lifetime of donor in absence of acceptor, and immediately you will get this value of k E t, and this value of k E t is nothing but tau d inverse r 0 by r to the power 6, and from here you will be able to calculate what is this r, what is the distance between the donor and the acceptor, right. Now, being said all those things, right, this is a theory, nice theory by Foster, somebody has to prove it that yes, really it is working, that once I change the distance between the donor and acceptor, the efficiency is really changing like that way, that is in the order of to the power 6, remember that r to the power 6. So, somebody has to prove it experimentally, right, and that that thing was done by taking a molecule like this way. This molecule looks like this, something over here, something over here, some molecular thing, fragments connected with each other, and you put D here and you put A here, right. This is actually a typical polypeptide change, right, with a little bit of rigidity, so that you know the distance here, because you are synthesizing, right. So, you know the distance over here, right. Now, if you look at this equation k E t equal to tau d inverse r 0 by r to the power 6, right, and you take ln on both sides, then I can write ln k E t is equal to, right, you understand. So, ln 1 over tau d, because this is tau d inverse, I took the ln, plus 6 ln r 0 and then minus 6 ln r, right. So, this is equal to, this is a constant, ln 1 over tau d is a constant, 6 ln r 0 is a constant because r 0 is a constant. So, some constant minus 6 ln r. It means that for such a molecule, if you can vary this distance, right, suppose you have prepared one like this and then you have prepared another like this, and you know in organic chemistry synthesis somehow you know what is this r, right, and you can vary r as per your desire, and at each molecule you are going to measure this k E t. How you measure this k E t? is easy. You just simply measure this lifetime over here as you seen here. So, you just measure this lifetime of this molecule, right, and you measure the lifetime of only the donor without this acceptor, then you measure this KET and then you plot this ln KET as a function of R, right, for several such kind of molecule. You should not change the donor acceptor, and that was done, right, to prove this Foster resonance energy transfer, whether it is valid or not. So, what you simply do? You simply plot this ln KET, right, and versus ln R, because you know all those things, and it was proved that the slope in this case is equal to a minus 6. The slope is equal to minus 6. That is it. It's already proved, right, that the whatever the Foster resonance energy transfer is actually operational. Is actually operational. But I will tell you one thing. When the people have studied this type of Foster resonance energy transfer, in case where the R value, the small r value is too small, people have seen that this is deviating from this type of equation, deviating from r to the power 6 dependence, and there the exchange interaction is more favorable compared to this Coulombic interaction between the donor and acceptor. These r to the power 6 terms comes in because of the Coulombic interaction. The orbitals are not overlapping with each other, but if it is so, why should they interact with this Coulombic interaction? The electron can jump from one orbital to another orbital. It is not necessary that Coulombic interaction will take place in this case, and that is the case of the electron transfer. And that is the case of the real physical electron transfer. And here because of the Coulombic interaction, the two are far apart and the interaction between two are taking place at a distance. This is because of the Coulombic interaction, right. So, they are different. Okay. Now, as I informed you briefly, let me show you that how this is helpful as a molecular ruler, right. So, typically I use the example of a protein. So, let me take a protein and draw it like this way. Like this way, and somehow you have some mechanism to label this protein with a donor and the acceptor. How, that is a different story, and I am not going to discuss that in this lecture, but it is possible. So, let us assume that you have attached one donor at this location and somehow you have attached another acceptor at this location. And if you take this donor and acceptor, right, this particular D and A, you will be able to calculate that capital R 0. That means, your capital R 0 known, capital R 0 for this D and A is known. If not known, you measure it because you know the form, right. Although I have not written explicitly, but any standard book you will get this form, right. So, you know this R 0. So, what you have to do now, and you also know this tau d, right, and you also know the tau d. What is tau d? Tau d is the lifetime of this donor in absence of the acceptor. That means, donor is alone, right, you have not labeled this A in this protein. Now, simply what you can do, you can just measure the tau dA, right. Once you measure the tau dA, immediately you will get 1 over tau dA minus 1 over tau is equal to KET, and KET equal to tau d inverse into R 0 by R to the power 6, and from there you can immediately tell the what is the distance between this D to A. You can immediately tell, right, no problem. Now, consider that this protein is undergoing some structural change, because you have heated the protein or you did something to this protein, and you change the temperature, you change the you decrease the pH or something like that. So, obviously, the protein structure will destroy, that is called the unfolding of the protein or denaturation of the protein, and as the protein will denature, it is expected that the distance between the donor and acceptor will increase, right. So, you can measure the distance between D and A, which will be a measure of the extent of unfolding of the protein. So, if you now plot the distance between D and A as a function of outside agent which will damage the protein, let us say for temperature, then you will get a clear idea how the protein is denaturating starting from its native state to the denatured state. So, this is a very nice example or very nice use of this Foster resonance energy transfer FRET, and where it is also called this molecular ruler. But here you notice one thing, during the calculation of this capital R 0, I said the value of kappa square is equal to 2 by 3, and I immediately took this 2 by 3 inside my constant. So, that capital R 0 is a constant. But do you really think that once this donor is attached to a part of a protein and then acceptor is also attached to another part of the protein, they could have random orientation? That means, the relative orientation of the donor compared to the acceptor could be anything? It is not possible. That means, probably it is not possible to use the value of kappa square equal to 2 by 3, and in the last few decades people are actually trying to understand that what is the specific role of this relative orientation when we will going to use this FRET in biomolecular system. Right. Suppose you have labeled some protein with only donor and some protein with only acceptor and some protein with both the donor and acceptor. So, this is the typical case of incomplete labeling. So, in case of incomplete labeling, what happen is some of protein are labeled only with D, no A, right, no A. In that case, what will happen? In that case, whatever the fluorescence intensity you expect to be decreased for a specific value of E, that much will not decrease, because some proteins they have only D. Now, in presence of A, I mean you thought that fluorescence intensity will be half, but for some protein they do not have A itself. So, those protein those has D and A together, their fluorescence intensity decreased to 50%, but those does not have this A, but only D, so their fluorescence intensity will not going to decrease 50%. So, that is the problem. So, I have to ensure that the protein which has D must has A, but that is very difficult for the ensure. But if I somehow know what is the ratio of proteins that has D, but does not has this A, if I know this ratio, then probably it is I can take into account. So, let us tell that the ratio of A by D is equal to, let us say, F A. So, then I can write F D A prime which is equal to measured intensity in presence of acceptor, which should be equal to F D A minus the quantity of fluorescence intensity originated from those protein which has only the donor, not acceptor, right. So, that is F D, that is my original fluorescence intensity, multiplied by 1 minus that factor Fa. So, if I know this Fa, then only I can write this, right. So, and F d prime should be equal to F d into Fa, that is it. So, that efficiency of energy transfer should be written as 1 minus F d A prime by F d prime, right. I do not measure F d A prime, F d prime. What I measure is I measure F d A and F d, that is it. I do not know what is F d A prime, F d prime, but somehow if I know this F A, this quantity, then only it is possible for me. So, this can be written as 1 minus F d A minus F d to 1 minus F A divided by F d to F A, which is equal to 1 minus F d A by F d to 1 over F A. So, you see I get this efficiency in this form, right. So, if you measure this efficiency just by this F d A by F d, then that will be a wrong answer, right. So, you need to multiply with this factor 1 over F A in this case, right. Okay, so, let us finish over here and we will continue our discussion on the next class. Thank you very much.